Hey everyone, and welcome back. Today we're doing a deep dive into deep learning.
Sounds pretty meta, right?
It kind of is.
Yeah.
But specifically, we're looking at image recognition, which is like how to teach a computer to actually see like we do.
Yeah, it's a problem that's really hard for computers, even though it seems so easy for us. Like, we just look at something and we know what it is. But getting a computer to do that same thing, that was a huge challenge for a long time.
Until this paper came along, the one we're diving into today.
Exactly. This paper is called Deep Residual Learning for Image Recognition, and it honestly kind of revolutionized the field. Before this, the world of deep learning had hit a wall. It was like every time researchers tried to build a deeper network, with more layers thinking that would make it smarter.
Backfire.
Pretty much. They actually started seeing worse results. They called it the degradation problem.
The degradation problem. Okay, so we're going to have to unpack that a bit. For those of us who don't live and breathe neural networks, why don't you walk us through it? Why would deeper networks suddenly start performing worse? It seems counterintuitive.
You'd think, right? More layers, more computing power, it should learn more, right? But the way these networks learn, it's all about those layers, those transformations.
Each layer learns how to transform the data in a certain way.
Exactly. So, in theory, the more layers you have, the more complex transformations it can learn, and the better it should do, especially on something as complicated as image recognition.
Okay, that makes sense. It's like adding more tools to your toolbox so you can build more intricate things.
Right. But here's where things went sideways. Researchers noticed that as they added more layers, those deeper layers, instead of building on what the previous layers had learned, they'd actually start doing worse.
Well, wait. So not just failing to improve, but regressing?
Yep. It was like they forgot everything they had learned, like a straight-A student suddenly forgetting basic math.
That's so bizarre.
Hmm.
And you're sure this wasn't just a case of overfitting? Like the network was just memorizing the training data instead of actually learning generalizable patterns.
That's a good question, and it's something they checked for. But no, it wasn't overfitting. The networks were just stuck. Imagine having all the best tools in the world, but not knowing how to use them.
Like those deeper layers were getting lost in the complexity somehow.
Exactly. And what was even weirder is that they couldn't even just match the shallower networks. Like, you'd think if a shallower network was already doing okay, a deeper one could at least do that well.
Right. Just copy what the first few layers are doing and then, I don't know, leave the rest alone, do nothing extra.
Exactly. It should be able to learn an identity function, basically outputting the same thing as the input. But for some reason, that was surprisingly hard for these deep networks to do. It's like they were overthinking it.
That's crazy. So deep learning hits this wall, the degradation problem, and nobody knows how to get past it. And that's where this paper, Deep Residual Learning, comes in.
You got it. They didn't just find a workaround. They totally changed how we think about building these deep networks.
All right, so tell me, what's the big idea here? How did they crack the code? So they had this degradation problem, deeper networks were choking. How did they even begin to tackle that? What was the big breakthrough?
Well, instead of making those deeper layers learn complex transformations directly, they thought, what if we just made them learn the difference from the original input?
The difference, so not the whole picture, just the changes along the way.
Yep, they called it the residual. Imagine trying to paint a perfect copy of a photo. Super hard, right? But what if you just had to paint in the scratches, the faded spots, the residuals?
I see what you mean. That's way easier.
Yeah.
So instead of the network trying to relearn the whole image at every step, it's more like you're giving it a shortcut, right? Just focus on the tweets.
Exactly. It's a much simpler problem for the network to solve. But how do you actually do that? How do you build a network that learns residuals?
Yeah, how do you make a neural network do that?
That's where shortcut connections come in. They're basically these little bypasses in the network architecture that let the original input skip over some layers and go straight to the output.
Wait, so we're not talking about a straight line of processing anymore. It's like information detours. That's pretty cool.
Yeah. And those detours are what let the network learn those residuals. Instead of each layer trying to go from the very beginning to the very end, they're just refining, adjusting, working with the differences.
And that somehow helps those deeper layers learn without getting confused.
That's the idea. It's like those shortcuts give the network a safety net. Even if some layers struggle, it can still fall back on those earlier representations from the shortcuts.
Ah, that makes sense. So you're preventing information loss as the data moves to the network.
Oh, clever.
But
Yeah.
adding all these shortcut connections, didn't that make the whole thing a lot more computationally expensive?
That's the best part. These shortcuts are dead simple. They don't add any new parameters or anything. It's basically just you add the original input to the output of the stepped layers.
So computationally, it's basically free.
Pretty much. And that's important because it let them compare these new residual networks, or ResNets as they called them, directly to the old plain networks. Same architecture, same computational cost. The only difference was those little shortcuts.
Okay, so they had this clever ResNet idea, but did it actually work? We're talking about the paper that revolutionized image recognition here, so I'm hoping it did more than just work.
Oh, it did way more than work. It absolutely crushed it. They got record-breaking accuracy, especially on this benchmark challenge called ImageNet. Have you heard of it?
ImageNet, yeah.
Yeah.
It's like the Olympics of computer vision, right?
Exactly. Millions of images, all labeled with different objects. If you can get your model to work on ImageNet, you know it can generalize to a ton of different images.
So winning on ImageNet isn't just bragging rights. It means you've created something really powerful.
Exactly. And that's what ResNets did. They didn't just win, they blew everyone else out of the water.
Okay, enough hype. Give me the numbers. How much better did they actually do?
All right, so they tested different variations of ResNets with different depths and compared them to the plain networks. And every single time, ResNets came out on top.
So deeper with ResNets really did mean better. They actually solved the degradation problem.
Solved it. And the deeper they went, the bigger the difference became. Their 34-layer ResNet was already way better than the plain 34-layer network. But get this. They managed to train a ResNet with 152 layers.
152 layers? Was that even possible back then?
It was unheard of. And remember, all this without running into the degradation problem.
So it was crazy deep, and it actually worked. It was better than anything they'd seen before.
Way better. This 152-layer ResNet even beat the performance of what they called ensembles, which were basically combinations of multiple models that people used back then.
Wait, so one ResNet was better than these Frankenstein models that combined predictions from a bunch of different networks?
Yep. Ensembles worked, but they were computationally super expensive. ResNets got even better results with one elegant architecture.
So it was faster, more accurate, and more efficient.
But weren't there other advantages too? Didn't they say something about ResNets training faster as well?
You're on a roll. You're right. On top of everything else, ResNets also converged way faster during training, meaning they reached their peak performance much quicker, which saved everyone a ton of time and computing power.
Okay, this is sounding more and more like the holy grail of deep learning. But we've only talked about ImageNet so far, right? Did they try ResNets on any other data sets?
Of course. They wanted to make sure it wasn't just an ImageNet thing, so they tried it on CFAR-10, which is another image data set, though a bit smaller.
Did it still work its magic?
It did. Big performance boosts there, too. But here's the really interesting part. They decided to get a little playful and see just how far they could push it. So they built a ResNet with over 1,000 layers and tested it on CFAR-10. 1,000 layers, that's just showing off. But seriously, could something that big even learn anything useful? I mean, CFAR-10 is tiny compared to ImageNet.
Exactly. And while this 1,000-layer monster didn't actually get the best results on CFAR-10, it was probably overkill for a data set that size. The fact that they could even train something that deep without hitting a wall was incredible. It really showed how powerful and scalable residual learning is.
So ResNets are crushing ImageNet. They're doing great on CFAR-10. They're even letting us train networks with 1,000 layers. It's like this one paper unlocked a whole new level of what's possible with deep learning. It really is amazing, isn't it? But hold on, we've only been talking about image classification so far, right? Like, there's a cat in this picture.
Right, that's just telling you what's in the image.
Exactly. But what about finding the cat in the picture? Like drawing a box around and saying, there it is right there. That's object detection, and it's a whole other ballgame.
Absolutely. Object detection is way harder. It's not just recognizing what's in the image, it's also about locating where those things are.
And I'm guessing they wanted to see if ResNets could handle that too, right?
Yeah. Oh, yeah. They weren't going to let ResNets off easy. They tested them on object detection as well, specifically on datasets like Pascal VOC and MS COCO.
COCO, I've heard of that one. It's like
Right.
the big leagues for object detection, right?
Yeah, COCO's tough. It's got tons of different objects, all kinds of cluttered scenes, and those objects can be any size, anywhere in the image.
So if your model can handle COCO, you know it's the real deal.
Exactly. And, you ready for this? The improvements they saw with ResNets on COCO were even more insane than ImageNet.
Okay, now I have to know. Spill the beans. How
Okay.
much better did they do?
So they took this standard object detection system called Faster RCNN.
Okay.
Faster RCNN usually uses a VGG16 network as its backbone. It's like
Yeah.
the part that extracts features from the images. So they just swapped out that VGG16 with their ResNet 101.
So same system, just a different engine, basically.
Yeah, and the results were ridiculous. Just by switching to ResNet 101, they got a 6% improvement in average precision.
6%. On a benchmark like Cocoa, that's huge, right?
It's massive, especially on a data set like COSO, where even tiny improvements are hard to come by. This really showed everyone that residual learning wasn't just some fluke, it was a fundamental breakthrough.
It's true. We're not just classifying images better, we're understanding them in a whole new way.
Yeah.
And they saw similar results on Pascal VOC too, right?
Yeah, not quite as dramatic as COSO, but still a significant improvement. It showed that this whole residual learning thing wasn't limited to just one data set or task.
So what started as this degradation problem, this weird roadblock in deep learning, ended up leading to one of the biggest breakthroughs in the field.
And it's crazy how far it's come. Remember, this paper was from 2015. Since then, residual learning has become like the foundation for so many deep learning models.
Seriously, everything uses it now. Self-driving cars, facial recognition, medical imaging, even natural language processing. Who knew that this one paper would have such a huge impact?
Right. And you know what I find so cool about it? It's such a simple idea at its core. Just learn the differences, not the whole thing. It makes you wonder what other elegant solutions are still out there waiting to be found.
It's true. Sometimes the simplest ideas are the most powerful. Well, this has been an incredible deep dive.
I agree.
We've seen how a seemingly small change can completely revolutionize a field and lead to these amazing real-world applications.
It really shows you the power of deep learning.
Absolutely. And to everyone listening, thank you for joining us on this journey. We hope you've enjoyed this deep dive into deep residual learning for image recognition as much as we have. And hey, if this paper blew your mind, go check it out yourself. You never know, maybe you'll be inspired to make the next big breakthrough. Until next time.